So good morning, everybody. I hope you all have had a good week and are looking forward to getting through Friday and having a reasonably relaxing to some degree weekend, even though, as I'm sure you guys are still in the middle of midterm madness. Today, I'm hoping to wrap up our discussion on compressible flow and work a couple examples in compressible flow. On Monday and Wednesday, we talked a lot about the basic principles in compressible flow and how it differentiates itself from incompressible flow, as well as took a good look at isentropic flow, particularly through nozzles. Today we're going to look a little closer at adiabatic frictional flow, as well as isothermal frictional flow. So we touched base on this briefly on Wednesday, which was adiabatic frictional flow. And we stated for adiabatic frictional flow, we have this friction term of interest, where our friction factor is an average of an inlet term and an outlet term over 2. Now, keeping in mind, if the Reynolds number is high, I would say probably Reynolds number greater than 3 times 10 to the 6 is probably a safe point. You can assume your N is F bar, because at that point you're at that region where your friction factor is going to largely level off. And you don't have to worry about variations too much with respect to velocity. And so we stated one of the biggest things we have to consider with this frictional term is the relative dissipation we expect given a Mach number in, or A, and a Mach number out. And we get the expression that looks like this: 1 over gamma times the quantity 1 over Mach number A squared minus 1 over Mach number out, or B squared, minus gamma plus 1 over 2 times the quantity of natural log of 1 plus gamma minus 1 over 2 times the quantity Mach number A squared. Oh, I forgot a term, crap. Mach number B squared times the quantity 1 plus gamma plus minus 1 over 2 times Mach number A squared over Mach number A squared times 1 plus gamma minus 1 over 2 times Mach number B squared. So all of that mess also is equation 649, I believe. Let me double check, make sure I have that number right. No, I was wrong, 638. So based on the expected friction and Mach numbers, we can identify frictional dissipation. You only need 2 of the 3 to get the third value. What typically we're going to look at is, given an inlet Mach number or an initial Mach number, we can solve for an approximation of the friction factor to get the outlet Mach number, and then ask ourselves if we have to adjust the friction factor based off of that Mach number at the outlet. And so it might shift your friction factor a little bit. And so there is a little bit of iteration involved depending on the friction factor that we see. Now, if we're interested, in determining the onset of choked flow, we can set our outlet Mach number, MAB equal to 1, which means our length becomes a maximum length or a maximum value before choke flow occurs, and we call this the maximum conduit value. And in this case, what we're literally looking for is if we have a large pipeline system, it's a good way to identify where the onset of choke flow occurs so that you can know where to put pumping substations to ensure you don't have choke flow within your system. And so if we set Mach number B equal to 1, we plug it into 638, we get the following expression here. Over gamma, 1 over Mach number A squared minus 1 minus gamma plus 1 over 2 times the quantity ln of 2 times 1 plus gamma minus 1 over 2 times Mach number 1 squared over Mach number 1, or A, I should say, squared times gamma plus 1. And this is equation 645 in your text. And I should say that's on page 148. And the equation that we talked about up here is on page 147. And I say it because, like I said, I don't expect you to be able to get everything easily from my handwriting. So I always refer to, when these equations get a little complex, I give you the page numbers. They're also found in the lecture slides. So given us an initial problem, one of the things that we'll look at is, based on a flow, we can identify the mass flux or the Mach number based on problem givens. So for adiabatic frictional flow, we can calculate the Mach number as a function of the mass flux by the expression here, which is g squared times mw divided by rho gamma tr, which also equals g squared divided by rho gamma pressure. And if we rearrange that solving for g, we can say g is equal to rho times Mach number times the square root of gamma tr over molecular weight, which also equals to the Mach number times the square root of rho gamma p. And I have a small mistake here. This should be gamma squared, rho squared. So I'm sure this looks a little like alphabet soup. So I think the best thing we can look at is an example of adiabatic friction flow. So you get an idea how to do this. Go ahead.
Can you zoom out or scroll up a little bit?
Of course.
Thank you.
Sure. Yeah, if I'm going too fast, let me know. I don't mind slowing down a little bit. All right, so let's take a look at that example. So we're looking at air flowing from a reservoir through a nozzle and into now a long straight pipe. The pressure and temperature in the reservoir are 20 atmospheres and 555 Kelvin. The Mach number is 0.05 at the entrance to the pipe. We're going to assume that's the values at the entrance to the long straight pipe. So the question then is, what is the maximum conduit length in the pipe before the asterisk condition is reached, and we end up with choked flow? All right, so let's take a look at what's provided. So we know for this example, the pressure inlet is 20 atmospheres. The temperature initially is 555 Kelvin.
You're still on the PowerPoint.
Oh, thanks. And the Mach number is 0.05 initially. Now, if we're looking for that length when we reach the asterisk condition, we're saying what happens. So when the Mach number B is 1, what is L, which is L max? Well, if we use equation 645, we should have everything we need to solve for this right-hand side of the equation. Because when we're looking at air, gamma is 1.4. So I'm going to throw you guys in some breakouts to see if you can work together to solve for the value in terms of the right-hand side of that equation. Doing that complex calculation to get F bar L max over RH equals a number, and that value will be dimensionless. All right, looks like almost everybody's slowly coming back. How did it go? How did it go, everybody? Did we get a value?
I have an answer.
All right, what's your answer?
I have about 280.
All right, 280 is correct. Well done. So, with that in mind,
I'm not sure what we do with this answer though, because that solves for F bar L max over RH.
equals 280.
Yeah.
Yeah, so for this problem, I intentionally left some values and information out. So what do we need to find a friction factor?
Reynolds number, K over D.
So we need a Reynolds number and a K over D. So we need to know something about GD over mu, correct? And so we're going to need a diameter. So what do we want the diameter of this pipe to be? I'll let you guys pick, make it a choose your own adventure.
0.1 meters.
You said 0.1 meters?
Yes.
All right, I got somebody that wants the meters. All right, and we'll assume stainless steel. So in meters, the K value for stainless steel is, let's see, 0.000457. 0.000457. So we need to solve for our mass velocity. Well, earlier I stated that the mass velocity can be solved knowing the Mach number and the square root of density, gamma, and pressure. So G is equal to 0.05 times the square root of the density. Now for this system at 20 atmospheres and 555 Kelvin, we worked an example on Wednesday that solved for that density, and it was about 12.7 kilograms per cubic meter. The gamma, air is 1.4, and the pressure is 20 atmospheres. Now, once again, we're going to end up with really strange units. So to correct for that, we have to convert atmospheres to pascals. And so 1 atmosphere is 101.325 pascals. We do that, and we're left with kilograms per meter squared second.
So we would normally have to solve for that density, right? We just plugged it in because we did it in another example.
Yeah, normally you would have to solve for the density, knowing density is P times molecular weight over RT. So we do this calculation, let's see, 1.27, or sorry, 12.7 times 1.4, 1.325. Hold the handy dandy calculator. And we got approximately 300.1 for our mass flux. So now with that, we can solve for a Reynolds number, which for compressible fluid, it's G times D over mu. And we're looking at air. And the viscosity of air, we can say now, admittedly, I am making this up, 5 times 10 to the minus 5th kilograms per meter second. In a real system, you would probably look that up. So we have 300.1 kilograms per meter squared second times 0.1 meters for the diameter divided by 5 times 10 to the minus fifth kilograms per meter second, which gives us our Reynolds number. Which I get about 600,000 for the Reynolds number. So now we have the Reynolds number. We can solve for a K over D value, which I said K earlier was 0.000457 divided by 0.1, which means I just move the decimal place. So now we have our K over D value and our Reynolds number. So then we use our equation, or our figure 510, to solve for our friction factor. Which for 600,000 and 0.0004, I get approximately 0.0042. So now we have that. We just need our hydraulic radius, which is our diameter over 4. So if our diameter is 0.1, our hydraulic radius is 0.025, which means that since we have F bar L max over RH equal to 280, that means L max is simply 280 times 0.025 meters divided by our F bar, which is 0.0042. Which I get approximately 1,667 meters. All right, so well, one thing here, in this problem, I assumed that F was approximately F bar. But if I was going to do this with more accuracy, I would have to solve for the friction factor at the outlet, or FB, which means I need a new Reynolds number to solve for that. So which value in my Reynolds expression is going to change between points A and B?
Would your mass flux change?
Your mass flux will not change because, once again, by the mass balance for a system at a constant cross-sectional area, that G will remain constant.
Shouldn't viscosity change due to temperature and pressure?
Yeah,
Changes?
the viscosity will change primarily due to our change in temperature. And so the most effective way to look at your change in viscosity is to find your new temperature, or the temperature that you should expect at TB. Well, from equation 643, TA over TB is equal to 1 plus gamma minus 1 over 2 times the Mach number of B squared over 1 plus gamma minus 1/2 times the Mach number of A squared. So based on that, what should we expect for TB? Well, what is 1 plus 0.4/2 divided by 1 plus 0.4/2 times 0.05? I got a value of approximately 1.188, which means T sub B is going to equal to TA over 1.118, or 555 Kelvin over 1.188.
Did you lose your squares?
Oh, thank you. I think I may have. So that value is slightly different. Oh, changed it by a percentage. Thanks for that. So I get a new temperature of 462.9 Kelvin. So with that in mind, do I expect my viscosity to increase or decrease?
Decrease because we cool down?
Now that's what I meant. So in general, if the temperature increases, our viscosity should decrease. So if my temperature decreases, my viscosity will increase. So now let's say that at T equals 462.9, my viscosity is now 9.7 times 10 to the minus fifth kilograms per meter second. My new Reynolds number then would be my mass flux times my velocity, or my diameter, 0.1 meters, over my new viscosity. Which should be about 314,000. I have the same K over D value, which was about 0.0004, which means based off our friction chart, our new friction value should be approximately 0.0044. Which means if FA is 0042, FB is 0044, then my average is just right smack in the middle, 0043. So it's going to change my final solution, however slightly. And so L max is now 280 times 0.025.
Can you zoom out just a little bit?
Yes. Divided by that new friction factor point. Let me clean this up. 0043. 1,628 meters. So not a huge difference, but it is a slight adjustment when looking at the average friction factor. The effect will be more pronounced when you have more drastic temperature changes. Any questions on that problem? Or do you guys kind of begin to see how to apply the equation for adiabatic frictional flow? Any concerns or points of discussion that you guys would like to bring up? All right, if not, I'll scroll back down to our new stuff. And now let's wrap up with talking about isothermal frictional flow. Now, when looking at isothermal frictional flow, one of the most pertinent things that we have to consider in this system is twofold. One, when we're looking at this system, now since we're allowing heat transfer to occur, in addition to being concerned about the frictional dissipation and pressure drop, P1, P2, we also have to keep an understanding of the anticipated heat transfer necessary to maintain a constant temperature. And so the first equation that we're typically concerned with is our pressure drop expression, which is equation 649 on page 150. And it looks a little like this. I'll keep using the A and B monikers. So we have PA squared minus PB squared equal to G squared RT over molecular weight times the quantity L of rho A over rho B plus our friction term FL over RH. I know now the book uses LB and LA, but we really don't care about those values. We want to know the relative distance between the 2 points. So I'm just going to stick to our friction term that we used in adiabatic frictional flow. One thing to keep in mind, there are a few forms of this expression. One of the more helpful ones for your homework particularly is in lieu of a ratio of densities, you can simply look at the ratio of pressures. By assuming an ideal gas, the ratio of densities and pressures will be the same. Another form that can be used is this one shown here, which eliminates the squares by instead looking at an average pressure. It's more useful if you don't have access to like a computer to assist in your calculations. But it is there for those that are interested. And that PB bar is just PA plus PB over 2.
Is that natural log of PA over PB or rho A over rho B?
It's technically both. The top expression is showing density, the bottom is showing pressure, or at least attempting to. Like I said, it's kind of hard to write P in rows in such a way that differentiates them.
Thank you.
But what I'm really trying to illustrate is you can use either the ratio of densities or the ratio of pressures. It'll give you the same value.
So the friction factor in these equations is not the average one that we looked at with adiabatic.
That's a good question. It is and it isn't, typically, because when we were looking at friction factor, right, we use Reynolds number and K over D to solve for it. And when we're looking at Reynolds number, we have mass flux times diameter over viscosity. Now for isothermal frictional flow, the temperature is constant, which means mass flux is constant, diameter is constant, and viscosity is constant. So the Reynolds number isn't going to change with this flow system, and neither is our relative roughness value. And since that's the case, the friction factor doesn't change, even though we have compressible flow. It's only for the condition of adiabatic frictional flow that we're going to need to look at an averaged friction factor.
Awesome, thank you.
You're welcome. One last thing to consider is heat flux or heat flow in isothermal frictional flow. And that is simply following this expression of Q over M, which is essentially a heat flow per unit mass. And that is equal to your mass flux squared over 2 times 1 over the density B squared minus 1 over the density of A squared. And I'll make those a little more in terms of densities. Maybe I should just use like a different color for density. Probably should have done that from the beginning. Oh well. This is equation 651. Page 151. So let's look at an example of isothermal frictional flow. So in this system, we have air at 1.7 atmospheres gauge and 15 C entering a horizontal 75 millimeter in terms of diameter pipe that is 70 meters long. Assuming the flow rate entering is approximately 0.265 cubic meters per second, and assuming isothermal flow, what is the expected pressure at the discharge end of the pipe? So what we're really looking for in this case is P sub B. So for this system, what we have is, I always like to start with either drawing a picture, writing our expression. For this one, we really don't need a picture, at least from my perspective. And what do we know? We know PA is 1.7 gauge, which is 2.7 absolute. One thing to keep in mind with this expression is you do want to use absolute pressures and temperatures. Temperature, as provided, was 15 degrees Celsius, which is 288 Kelvin. The molecular weight of air, as always, is 29. What do you guys want to use? grams per mole, springs per mole. We can use guacs, guacamole. R for this system, what do we got? Atmospheres. So I'm going to use probably 0.08205 cubic meters, atmospheres per kilomole Kelvin. And the L provided was approximately 70 meters. And our flow rate was 0.265 cubic meters per second, with a diameter of 75 millimeters, which should give us 0.075 meters. So looking at our expression and what we've given, the one thing we don't have, as always, is our friction factor. So we need to solve for our friction factor, which means, once again, we're going to have to go down the Reynolds number rabbit hole, or GD over mu. Well, we don't have G, so we have to solve for our mass flux. G is equal to our mass flow rate over our area. We have our volumetric flow rate. So if we know our volumetric flow rate, we can solve for our mass flow rate as our volumetric flow rate times our initial density. So rho naught is equal to P naught molecular weight over R T naught, or 2.7 atmospheres times 29 kilograms per kilomole over our R value, 0.08205 cubic meters, atmospheres per kilomole Kelvin, with a temperature of 288 Kelvin. As always, we can do a quick temperature unit check, and we're left with kilograms per cubic meter, which is a good sign. We get approximately 3.31 kilograms per cubic meter for our density. Now that we have our density, we can solve for our mass flow rate, which is our volumetric flow rate times our initial density, or 0.265 cubic meters per second times 3.31 kilograms per cubic meter, which equals about 0.878 kilograms per second. So now that we have our mass flow rate, we can solve for our mass flux, which in this case is going to be our 0.878 kilograms per second divided by the flow area, or pi times 0.075 meters squared over 4. Which gives us approximately 199 kilograms per meter squared per second. So now we have our G value. The only thing that we need now to find our Reynolds is our viscosity. Looking up our viscosity, we can get a value of approximately 1.74 times 10 to the minus 5th kilograms per meter second. So our Reynolds number is approximately 199 kilograms per meter squared second times the diameter of 0.075 meters over our viscosity of 1.74 times 10 to the minus 5th kilograms per meter second. Which should give us a value of approximately 857,000. So now, after all of those calculations, we finally have our Reynolds number. With that in mind, we can look for our relative roughness. It's a steel pipe, so it's 0.00015 feet divided by 3.28 feet per meter divided by 0.075 meters. And we end up with a relative roughness value of approximately 0.0006. So with this in mind, now we have a Reynolds number, now we have our relative roughness value, and we can solve for our friction factor. Our friction factor from our figure is about 0.0044. And so we just did a whole lot of work for one term in our expression. But now, looking at our expression, we know this value, this, and this, where we can solve for the hydraulic radius. It's just 0.075 over 4, which is approximately 0.01875, or 0.0188 because sig figs. So that leaves us with solving for our outlet pressure. Now, the issue that we have in this is the outlet pressure is both on the left-hand side and on the right-hand side, which means there's no easy analytical solution for this expression. So what I recommend when looking at this equation, because you're going to use it a couple times for your homework, is typically what I usually do in these situations. So I'm going to say, oh, I got a chat question, hold on. I would set this equal to some value. I call it the left-hand side. And then I set this value, which is all of this gobbledygook, equal to a value by guessing your outlet pressure. Then what you can do is you basically guess the pressure, you end up with a value on the left-hand side, you guess the pressure, you get up a value on the right-hand side, so you end up with two values. If you set up a cell that is equal to the left-hand side minus the right-hand side squared, you can tell solver to minimize the value in this cell. By guessing PB. And this is called the least squares minimization technique for iterative solutions. It's a really helpful method of doing iterative solutions to hone in on the true solution in a very short amount of time. So that's what I recommend when doing these calculations. Just be careful and make sure you have your units aligned properly, as the G squared can mess people up, particularly if a problem asks for values in English units. So if you do that and you set up the iterative solution and you ask solver to give you that final value, you'll find PB is approximately 1.98 atmospheres absolute. All right, any last minute questions on compressible flow? All right, if not, that's all I have for you guys today. I want you all to have a great rest of your day as well as a wonderful weekend. I'll pop over in a few minutes over to office hours. I know I've got quite a few emails last night in terms of homework questions and solution checking. So I'll try to dig through that while I'm in office hours answering questions for people. And if you need anything, don't hesitate to reach out. But if not, take care, guys, and have a great rest of your day. Thanks for coming.